In this example, we're being asked to compute the section modulus and the radius of gyration about the centroidal x-axis for the shaded area. So in this diagram, we have our global Cartesian xy coordinate plane, and we have a curve here that is given by this function y equals 1 over 32 x cubed, and it has boundaries across the x-axis of 4 inches. So this is bounded by the origin and 4 inches on the global x-axis, and then it's bounded by the origin and 2 inches in the global y-axis. And so we have this kind of shaded area right here that you see my shading is already there in yellow. So before we actually tackle the nitty-gritty details of this, under solution, the first thing I'm going to write is my formula for section modulus and radius of gyration about the centroidal x-axis. So let's look at section modulus. So the section modulus about this centroidal x-axis is going to be s sub x equals I sub x over y bar. And then the radius of gyration about the centroidal x-axis, r sub x, is going to be equal to the square root of I sub x over the shaded area itself. Now, the thing to note here is that the subscript x, in this context, x indicates the centroidal x-axis. All right, so it's not actually talking, oops, didn't mean to erase that. It's not actually talking about this x right here. It's really talking about the centroidal x-axis, which is going to be somewhere right here, okay? And remember, the centroidal x-axis is defined by the centroidal ordinate y bar, okay? So what this is telling you is that we're going to need to get some information about y bar. And if you just look at the two governing equations we have for section modulus and radius of gyration, we need to get y bar in there. So there's really 3 components we need to solve for what we are being asked. We need I sub x, which shows up in both formulas. We need y bar, and then we need the area, the shaded area itself. Let's start with something kind of straightforward. Let's go ahead and get the shaded area itself. Well, how do we get the shaded area here? Well, that's pretty straightforward. We're going to say area is just the integral, right? So we can go integral from 0 to 4 inches of y dx, okay? And we know what y is. We were given that function. That's 1 over 32 x cubed. So we can just go ahead and say this is equal to the integral from 0 to 4 inches of 1 over 32 x cubed dx. So this should be a pretty straightforward integral. You could do this by hand, or if you have your TI 36X Pro calculator, you can go ahead and punch that in your calculator fairly easily, and you should get this is equal to 2 square inches. So that is part of what we need. Here's the A right here, so we got that, no problem. The next thing we can go ahead and get is y bar. Now, if you remember from chapter 9, y bar, the integral form of y bar is going to be the integral over some area of y tilde dA divided by the integral over some area dA. Okay, and that goes back to chapter 9. Now, how do we set this up? Well, I would recommend to get y bar, let's make a note here. I would say let's use vertical slices to get y bar. So if you remember from chapter 9, if we set up, let's change colors here. Let's set up a vertical slice right here. Okay, and that vertical slice is dA. So that dA is going to have a little width of dx. And if you remember, y tilde is basically represented by the centroid of that vertical slice, okay? So in this case, since y tilde is going to be measured from the global x-axis up to the curve itself, y tilde should just be equal to y over 2. That's just going to be, of course, the function value y divided by 2, okay? And so, you know, all we do is we say this function value over 2, and that is clearly going to become 1 over 64 x cubed. You just take that function divided by 2. That's it. So coming back down here, and again, this should be kind of a review for you, to be honest with you, but coming back down here, we'll get y bar equals integral, and it'll be over the area, and we just said y tilde is y over 2. So we can go ahead and write this out a little more explicitly, y over 2. Now dA, what is dA? Well, if you're taking vertical slices, then we can say dA is equal to what? Well, it's y dx, okay? It's the height of the rectangle, which is a height y measured from the global x-axis, times the little differential with dx, okay? So coming back down here, we're writing our integral. dA is going to be y dx, and then, you know, we still have the integral of the area right here. Now, let's go ahead and you know, substitute values in. So because we are now integrating with respect to dx, a horizontal differential element, we're going to integrate horizontally across that x domain, which was 0 to 4 inches. So this integral is going to be 0 to 4 inches. And then y over 2, we already figured that out, is 1 over 64 x cubed. And then y is 1 over 32 x cubed. And then we have dx, and then all divided by, let's clean up some of these little dots I sprinkled around here. And then we're going to say all divided by the integral from 0 to 4 inches. Again, y dx, you know, this right here, you could write this dA is y dx now. So written as y dx, that's, of course, 1 over 32 x cubed dx, okay? And so if you carefully evaluate this integral, you can put it in your calculator, you could do it by hand. Because this is a review, I'm just going to go ahead and tell you what this this fraction becomes. I get 0.571 inches. Now go ahead and double check me, because I mean, I did this by hand and I did it in my calculator, but you know, on a test, on a final exam, or on a quiz, you would have to evaluate this on your own. You would have to know how to do this. I'm not going to just tell you what the answer is on an exam. So you maybe pause the video and crank through this and make sure you get the same thing as me. All right. So there's y bar. So we have another piece of one of these equations that we need. The last thing we need is the moment of inertia about the centroidal x-axis, I sub x. Okay. So again, we know that I sub x is going to be equal to the integral over an area of y squared dA. All right. Now, if you recall from some previous videos, I gave you a recommendation. I said when calculating I sub x, or an I value in general, it's best to look at slices parallel to the axis you're interested in. Okay, so we'll make that note again. We're going to say for I computations, it is best to orient slices parallel to the desired axis. So that should be in your notes from an earlier video, but that's just a little reminder, okay? So so you know, it may be a good idea to redraw this just for clarity purposes. So here's the whole picture again. Okay, and you know, this was y equals 1 over 32 x cubed. And you know, here's our shaded region. And here is 4 inches. here is 2 inches right there, okay? So for this particular problem, we said let's look at horizontal slices. And again, that's based on what this little star is, this little asterisk. Orient slices parallel to the desired axis. So when you look at this, you need to kind of do a little bit of repackaging here, okay? So first, let's look at DA. What is this DA going to be? Well, this area DA is going to be something times DY. This little height right here is DY. What is this little green dimension right here? Is it 4 inches? No. Is it X? No, not quite. Remember, X is going to be an arbitrary distance measured from the origin. So the width of this rectangle should be what? 4 minus X, 4 inches minus X. So our DA in this problem is 4 inches minus X times the height of that little slice DY. So maybe take a second, pause, look at some extra problems in the textbook in chapter 10, and make sure your confidence in what we're doing here is up to par, okay? So this is DA. So now we can kind of more completely write this I sub x formulation as the integral over an area of y squared, and then DA is 4 inches minus x dy. So now if you notice, we're taking the integral with respect to a differential height dy. So what do we need to do? Well, we need to rewrite this x value as a y variable, okay? So we'll make a little note here. We're gonna say write the variable x in terms of y, okay? Well, all you need to do is look at the function right here. You already have y as a function of x, so we're going to do a little bit of rearranging of this function, and we're going to get x as a function of y. So if you just cross multiply and take a cube root, you're going to get x equals 32y cube root, okay? Or, you know, if you like writing it this way, this is fine too. Okay, so the cube root of 32y, and that's just very simple algebra to make that little rearrangement. So finally now we can write I sub x as the integral from 0 to 2 inches y squared times 4 inches minus cube root of 32y dy. Okay, now this looks a little daunting, and again, this is 4 squared right here, so maybe not 4 squared, I'm sorry, it's 4 inches right here, so put the little inch mark there. So I know this looks a little daunting. I'm okay if you put something like this in your calculator. I mean, you can do this by hand. They're essentially, it's still a basic polynomial type of function, but you can put this in your calculator. Now, double check me, but when I put this in, I get this whole thing equals 1.07 inches to the fourth. And I directly put that into my TI-36X Pro calculator to solve that integral, okay? Well, now we have all the pieces that we need. So if you're ready to go, we can say the section modulus about the centroidal x-axis. These are about the centroidal x-axis, not the global x-axis, is going to be I sub x over y bar. So we have 1.07 inches to the fourth divided by, what do we get for y bar earlier? 0.571 inches. And we get 1.87 inches cubed for s sub x, and that is definitely one of our answers. That's the section modulus about the centroidal x-axis. And then we need the radius of gyration about the centroidal x-axis is square root of I sub x over the cross-section area. So we would say this is the square root of 1.07 inches to the fourth. Track these units for me. And I think area we got earlier is 2 square inches. Let's scroll on up and double check. Yeah, there it is, 2 square inches. So we can evaluate this, and I get 0.731 inches as a radius of gyration. So check those units, but units of section modulus are length cubed, and units of radius of gyration are just length. So that is the end of this example.